Hello students, this is Professor Unking, and this is to cover the concepts in Chapter 14 of Work, Energy, and Power. So let's go ahead and get started. Just to provide you a little refresher and example, let's recall that work, and we designated, or at least the book designates that as U equals force times the distance, or U equals F times S. Now, of course, work is expressed in joules, 1 Newton meter, or a foot-pound. Let's look at an example. So we have our inclined plane with a 30-degree angle, and of course we have our block on our inclined plane. And what we want to do is move this block 3.5 meters up the inclined plane. Now the mass of the box is 150 kilograms. And we want to find out what the applied force that is necessary to move that box up that 3.5 meters. So what is the required force P to push the box up the inclined plane, and how much work is required then to push the box up the plane, assuming that the plane is frictionless? So let's go ahead and examine this in more detail. So here's our box on our inclined plane, and of course we know that we have a weight component of the box going straight down to the ground. And if we were to calculate that weight, it would be mass times gravity, or 150 kilograms times 9.81 meters per second squared, to give us a weight of 1471.5 newtons. Now, as you recall, whenever we're dealing with an inclined plane, we have to break it into its two components. One is this component, which we will call the Fy component, which is the weight times the cosine of theta, or 1471.5 times the cosine of 30 degrees, or 1274.36 newtons. But we also need to know the weight component that is parallel to the surface. And that is we'll call that f of x, which is the w times the sine of theta, or 1471.5 times the sine of 30 degrees, or 735.75. Now keep in mind, that is the force. That's the necessary force that we have to overcome in order to move this box up the inclined plane. We have to have at least a minimum of that. So if we look at the analysis, that force of x is 735.75 newtons is the minimum applied force to move the block up the plane. And we know that work is the force times the distance, so 735.75 times 3.5 equals 2575.13 Newton meters, or joules. Alright, so let's get on to another thing that we somewhat touched on previously, which deals with the variable force. And when we're talking about variable forces, we're dealing mostly with a spring. Now, the force equation for a spring is force times k times x, where k is the spring constant and x is the change in length of the spring, whether you're compressing it or pulling it. The units for the spring constant are either Newton per meter or pound per inch. Now for a spring, work is still designated by force times the distance, but in this case S is x, so the equation becomes U equals F times x. Now keep in mind that whenever we're dealing with springs, we're moving springs in different directions at all the time, so we have to calculate the average force. We don't have one specific force that's being applied to the spring at any specific time, so we multiply that by the x. So the average force would be like 1/2 the force, or the change in force, times the x, and substituting the F equals kx into the force part, we get 1/2 k times x, or U equals 1/2 kx squared. So let's look at an example. So we got our spring, and I would say that it has a spring constant of 3 kilonewtons per meter. We apply a force to the outside, kind of like you lying on your bed, and it compresses the spring 55 millimeters. So what I want to do is find the work that is being put on this spring, or how much work the spring is actually being applied to whatever body is being placed against the spring. So we have the U equals 1/2. Take 3 kilonewtons per meter, which is 3,000, times 0.055, which is the distance that the spring is being compressed, and square that. And we get a value of work to be, or of energy to be 4.54 joules. Okay, so that's the work that's being done on the spring. Now, chapters 14.4 and 14.5 basically talk about potential and kinetic energy, and also the conservation of potential and kinetic energy, or just conservation of energy. So potential energy, as we talked about in the last class, is the ability of an object to do work based on its distance from the ground. So the potential energy is going to be the weight of the body times some distance h from the ground, or mgh. Now, kinetic energy is the amount of work being done by an object that is moving, or kinetic energy equals 1/2 mv squared. So let's look at an example. Let's calculate the kinetic energy of a 3 kilogram object moving at a rate of 3 meters per second. So knowing our kinetic energy equation of 1/2 mv squared, just substituting, we get the mass of 3 kilograms, and of course we square the velocity of 3 meters per second to give us 9, and the kinetic energy therefore is 13.5 joules. But what if I wanted to find out what would be the equivalent height of an object with the same amount of energy and the same mass? So basically what I'm trying to do is, if I had an object that I'm suspending in space, I want to know how high do I need to suspend at to have the same amount of energy with that same mass. So if I were to pick that mass up after it's stopped on the ground, how much energy in terms of potential energy would be equivalent. So we want to find out how high I have to lift it off the ground. So potential energy, of course, is the mass times the gravity times the height. We know that the kinetic energy, and we're conserving energy here, so we're going to use the same exact value that we had found for the kinetic energy of 13.5 joules, and we're going to multiply, or let that equal to 3 times 9.81 times the h. Solving for h, we get 0.46 meters, roughly a half a meter. Now going on to chapter 14-6, we're going to be talking a little bit about the angular aspect of kinetic energy. Now let's recall the equation for linear kinetic energy. We just found that to be 1/2 mv squared. Also recall from previous chapter 11, we have velocity equals r times omega. So if we substitute this r omega in for the v in the kinetic energy equation, we get 1/2 m r omega quantity squared, which gives us 1/2 mr squared omega squared. Now, we recall that if to find the total mass moment of inertia, we get the sum of all the mass times the r squared, which gives us I, which is the mass moment of inertia. So we can find that kinetic energy with respect to rotating objects becomes 1/2 I omega squared. Now keep in mind, kinetic energy is still in joules, omega is in radians per second, and I is in kilogram meters squared. Let's look at a quick example. So we have a woodworker trying to turn a piece of circular piece of wood on a lathe at 125 RPM. Now the wood has a diameter of 275 millimeters and has a mass of 315 kilograms. Let's find the kinetic energy of the piece of wood. Now, of course, as you well know by now, once you see RPM, we're going to go ahead and convert that into radians per second. And just by knowing that we have 125 revolutions per minute, we multiply that by 2 pi revolutions, or radians in 1 revolution, and then we have 60 seconds per minute. And multiplying by that number, we get 13.09 radians per second. So we're going to use that value later. So also recalling from table 9-2, since this is a circular piece of wood, we know that I sub c equals 1/2 mr squared. And so we just substitute 1/2, and then 315 is the mass, times the r value, which is the radius. Notice that the diameter is 275 millimeters. So we need to not only divide that by 1,000, but then we also need to divide that by 2 to give us the radius. You square that value, so our mass moment of inertia becomes 2.98 kilogram meters squared. Substituting that into the kinetic energy equation, we get 1/2 IC omega squared, which is 1/2 times 2.98 times 13.09 squared, which gives us 255.31 joules. Now, some equations you got to remember when you're doing some of these problems. You got to recall the stuff from chapter 11. Things like the distance equals the radius times the theta. It's conversions from linear to angular, or vice versa. Velocity equals r omega. Your tangential acceleration equals r times angular acceleration. And a new equation, which is the work done in something rotating, is the torque. And we all know what torque is. It's just a force times the distance times the theta. Now we're going to move on to chapters 14-9, talking about power and horsepower. We're going through this chapter pretty quickly, but it's important that we go ahead and get these concepts underway. Now we're going to introduce the concept of time into the mix of energy and work. When we do this, we can now talk about power, which is basically the rate of doing work. So if we look at the equation, power equals work per unit time, which is force times distance over time, or power equals U over T. And the units for power are either in watts or foot-pound per second. It could be joules per second, and a joule per second is a watt. So that helps you in understanding things like whenever you're using power in your house, how they rate a lot of your power usage in kilowatts. So in kilowatts, just 1,000 watts. And we can also discuss horsepower, which is by definition the equivalent of 1 horsepower is 550 foot-pound per second, which is 33,000 foot-pound per minute. From an equation standpoint, we can convert power and horsepower equals force times the distance over 550 times t, and this equation you only use when we're given t in seconds. But if you're given t in minutes, you get force times distance over 33,000 times t. Force times distance over 33,000 times t for t equals in minutes. And the last concept is torque and efficiency. So let's recall that that previous equation, that U equals torque times theta. So therefore, our power equation then becomes U over T, which is torque times theta over T, which is torque times theta over T. And we all know that theta over T is just omega, so that's torque times omega. So you can calculate the power of any rotating system as long as you know the torque and know the angular velocity. And also know that we can convert from horsepower into kilowatts by knowing that 1 horsepower is 0.746 kilowatts. Now as for efficiency, this is just calculated by the ratio of power output to power input, or efficiency in percentage. You get the power output over the power input times 100. So your answer comes out in a percentage. Well, this is pretty much it. If you have any questions, feel free to send me an email or bring them to class next time we meet. Otherwise, you have your 2 sets of problems that are in Blackboard. Go ahead and work on those, and then we can go ahead and see if you have any questions regarding that. Otherwise, we're going to move on and try to see if we can capture some of the concepts of Chapter 15. Thanks, take care, and have a great day.